Now we will define value functions. So value functions are nothing but it's basically the value function for a Markov random process is nothing but it's the expected value of the return. So we have already discussed this. That is why we need an expected value of the return. We need an expected value of the return because for different paths, your returns are different. So we want to find an expected value of this random variable. So that's why we define that expected value of the random variable of the return for a particular state S, and we are defining that value as state value function. So this is basically called as a state value function and it is denoted by Vs. So let us say if I have a maze grid problem like this. So this is the first grid word problem, and then this is the second grid word problem. So if we can actually evaluate the returns, that is the expected value of the returns for each of these states which are given over here. So what I'm trying to show over here is that what is the physical interpretation of this value functions which we will be trying to calculate here. So the physical interpretation is that we have two solutions for this. One is this and another one is this. The question is that which one is the better one. So obviously the right one will be the better one because the returns that you are getting for each of these individual states are greater than the returns that you will get in this particular solution. So here if you see on the left side, for each of these states, the returns that you are getting are less as compared to the returns that you are getting onto the right side. Once you calculate these values, then you will realize that these values will be helping us to move our agents in a specific location, which we will discuss later. But the important thing is these value functions it's basically helping the agent to move into the specific location in which it wants to move in order to maximize the returns. So the right grid is favorable because it is getting maximum rewards in each of these states as compared to the left one. We will understand all this later on in more details, but this is the physical interpretation that why we want to have value functions in first place. So the value functions are basically directing the agent to move to a specific location in an optimal way. So we will understand all these things later on in more detail, but for now you can understand that value functions are nothing but it's basically the expected value of the rewards. So as I was telling you earlier, basically value functions can be calculated using two different approaches, that is using multiple episodes, which is the one which we had discussed in this case. Here we used two episodes. This is the first episode, this is the second episode, and we had taken actually 5 steps in this episode, and here we had taken again 5 steps in this episode. So now basically I am repeating this example again just to make you understand how to calculate these value functions. So now if you see, this is the different MRP process which I have given here. So we have 4 different states, and for each of these states we have r equal to 1 reward. For this being in state 2 you have r is equal to 2. For being in state 3 we have r is equal to 3. For in state 4 we have r is equal to 0. And note that this reward is r of s and not r of s comma s prime as it was in the earlier case. So note that, it's important. So now the important thing is we want to reach to the final destination which is S4, and we are starting from S1. So there are multiple ways of reaching S4 through S1. The first is either going from 1 to 4 straight. The second path which I am writing as E2 is basically going from 1 to 2 and then to 4. This is the second path. The third path will be from 1 to 2 to 3 then going to 4, which is defined by this. And the fourth path is basically going from 1 to 2 to 3 and again moving in this 3 2 times and then going to 4. Note that for each of these paths that we have, basically we have 4 episodes here, and in each of these episodes the capital N value is different. So here N is actually 1, here N is 2. So for each of these we have different values of N. If I want to calculate the return of state 1, which we are defining as g of 1 here, that value will be 1 for this particular path. If I want to calculate the return g2 basically of state 1 only, then this will be calculated as 1 plus gamma which is taken as 0.5. So 0.5 times the reward of being in state 2 when you move from state 1 to 2. So you will get a reward of 2 here. So that's why it's 2 here. And then 0.5 square times 0, because we are moving from state 2 to state 4. The reward for being in state 4 is 0. So that's why 0 is here. So you will get a value of 2. Similarly, you can calculate the reward of being in state 1 again. Basically return for being in state 1, and this is basically the third episode that you are running. So all these values which are given in bracket are the episode values. So if you calculate it, its value will come out to be 3.75. Similarly, for the fourth episode, if I want to calculate the return for being in state 1, its value will be 4.13. So now if I want to calculate the value function, which is nothing but the expected value of the return for being in state S, then it can be easily calculated using the summation divided by 4. So it's a average value that you will calculate for calculating the value of being in state 1. So that value comes out to be 2.72. So you can see that you need larger number of episodes to basically approximate the expectation value which is given over here, because this is simply a Monte Carlo estimate of the expectation operator. So in order to reach to the actual value of the expectation, you have to go for large number of iterations. So this is the first way of calculating value state function of a particular state, that is using multiple episodes, as we had done in this particular example. The second way of doing it is through Bellman equation, which we will discuss now for Markov random process. Note, it's for Markov random process and not for Markov decision process. So there will be some changes here. So in the second episode, so that the second way of solving this particular problem here, we do not want to go for larger episodes. So the second way of solving this problem is through use of Bellman equation. So let us see what this is and how we can use it for solving the value function for a specific state. So we know that we have to do large number of episodes in order to approximate the expectation operator. So we want to avoid this situation. So in order to solve this problem, what we are doing is we are actually using Bellman equations. So Bellman equation is nothing but it is a recursive equation, and we will see how we are deriving it. So value of a particular state is basically nothing but it's an expected value of the return for that particular state, that is given that state S. And now what we are doing is we are actually writing the definition of GT here. So if you recall, our GT is nothing but let me go back to the slide here. So our GT is nothing but this expression here, right? So we can use this expression this side. So you can see we can write this expression here, given this state st is equal to s. Now what we are doing is we are just rearranging the terms. So we are keeping the first term intact, whereas the gamma is taken out from the second terms, and we are rewriting this series again. And note that this is again, we can write it in terms of the gt plus 1, because here you can see gt is gt plus 1 plus gamma times gt plus 2, gamma times rt plus 2 plus gamma square rt plus 3. So if I increment it by 1 here, so this will be 2 and this will be 3 and this will be 4. So that's why I can write this particular series with gt plus 1 instead of t. So you can replace this by a factor of gt plus 1. Now the important thing is, we can write this gt plus 1 as value function of the state st plus 1 given st. So this is basically a bit difficult to digest, because you can see that expectation is inside this gt plus 1, and then for that case you have a value function. But here expectation is still outside, and even after that we have a value function inside. And the another important thing is, so the value function is basically defined for a specific time t. So in both the cases the time t is same, whereas in this case you have actually time t plus 1 here, and this is the state at time t. So how come it is possible to replace this by a value function here with time t plus 1? So these two things are worth mentioning out here. We will address these 2 points in our coming series. We will be deriving the Bellman equation from scratch. So at that point I will discuss this, but for now you can assume that we can replace gt plus 1 by the value function at that state st plus 1, given st equal to s. So now what we can do is we can actually split the two components. So the first component is this and the second component is this. So the first component that we have here, if you recall, it is similar to this. The only difference is now here it is RT plus 1 and here it is ST. So recall, let me copy this just to make you aware that both of them are same and paste it here. So you can see now both the equations are same, but only the difference is that here it is RT and here it is T plus 1 and here it is T minus 1 and here it is ST. So you can actually increment T by T plus 1 and you will get the same expressions. So whatever is written over here will actually be applicable here also, like for these two terms. So you can see both of them are same. So let me copy this from here so that so you will understand what I am saying. So if I copy it here, then you can see both of them are same. Here you have reward, here also you have reward, here you have this transition function which is the same as this one. The only difference is we have these two summations here. So what we can do is we can actually replace them by a single summation with the r and s prime, and then we know that r is a function of s and s prime. If it is a function of s and s prime, then we can write it like this times this. So this is already the same as, and the second one is the gamma times the expected value of this, which you can take it right now as basically gamma times the probability of this times the value of the next states. So what I am saying is, if you want to calculate the expected value of some variable, let us say v here, for the next state, it is nothing but the summation of the x times p of x, right? If it is e of x, then e of x is nothing but x times p of x. You are summing it up to get the expectation. So here what you have, x as v of s prime, and what is there, the probability of v of s prime. So what we are saying is that the probability of v of s prime here is this one only. So we will understand why this probability of v of s prime is probability of this, which is given over here in our coming lectures. But for now you can assume that this probability of v of s prime is this transition probability of the Markov random process. So this equation can also be understood from the from a diagrammatic point of view. So let me explain this here. Let me copy this first. So this is called as a backup diagram. So here what we are saying is value of a given state S is given like this, as we have already seen. So now this is state S, and for this we are calculating the value of the state, and then you know that based on the transition probability that you have, that is you are moving from S to S prime, we have different transitions, like we are going to from S to S double prime, you are going with this transition probability, and to be specific it will be S double prime here, and from here to here you are going it with the probability which is given over here, the transition probability, and also the reward which is defined as S, and in between S and S prime, that is the current state and to the next state, is given like this. And why it is double dash here? Because you are moving from S to S double dash, so the reward corresponding to that is here, and similarly the reward which is in between S and S prime is here. So now if we want to calculate the expectation of this node S, that will be given by the probability that you have. This is the transition probability in between the node S and S prime, S double prime, times the value of this node. So we are assuming that we have already calculated the values of these nodes, the bottom nodes here, and they are denoted by V S double prime and Vs prime here. So if we know the values of these two, then the expectation of this node can be easily calculated by multiplying the individual values with the corresponding transition probabilities. So that is what is given over here. So we are actually multiplying the values of the next state. That's why it is given as S prime here. So we are taking all the states that we have in the lower node. So there will be multiple states like this. So we are actually considering all of them, and all these contributions are incorporated in this summation, where we have a summation for S prime. So that's why we are actually we assume that all these states will be having these value functions calculated already, and then we are actually weighting it by a factor of gamma, because this is the next state with the value function. So we are weighting it by a factor of gamma, the discount factor, and then it is multiplied with the probability distribution, multiplied with the transition probability, which is given over here and here, and we will have multiple such transition probabilities for different states. So this is for the second term that we have here, along with this transition probability. For the first term is basically the expected value of the rewards here, which we have already calculated in our earlier slides. So the important thing is to understand these two terms, which can be understood from the backup diagram which is given over here. So what we are doing in nutshell is we are calculating the value of the state S by already knowing the value of the future states, which are multiplied by a factor of gamma, and then with the transition probability given by this. So now if the rewards depends upon the state S only and not on S and S prime, as we have discussed earlier also that there are two types of rewards that we found in literature. So if that is the case, that is your rewards are depending upon the state S only, then what we can do is we can actually reduce this to this, and now we can observe that this summation is on S prime and not on S, so RS can be taken out. So if RS is taken out, then what we can do now is we can write this value state function as this. So the RS can be taken out easily, because RS will have summation on all these states and rewards for this particular term, and if you do the summation on all the possible states and rewards, the probability function, this value will be 1. That's why we have RS here as an individual case, when R depends only on the state S and not onto the transition S and S prime. So this is alternative way of representing the value function, and the corresponding backup diagram for this case will look like this. And here you note that the rewards RS are denoted over here rather than showing it onto the transition diagram. So this is the reward for being in state S, and it's denoted by this in backup diagram. So now we have understood how to calculate the value function. So let's come back to our original question from where we started out, and the question is how to calculate this value of V1 using this Bellman equation. So we saw that we can calculate the value function for any state ST as this. We already know this. So let us see how we can, we already know this expression, right? So we know how to calculate any value function for a given state using this equation. So let's write this equation in matrix form and see whether we can easily calculate the value functions without going for multiple episodes using this equation or not. So what we can do is we can actually write this in a matrix form, which is given like this. So here PSS is the transition probability, which is given over here. So this is written in this matrix form, and the value function the V, and then we have this R, which is the reward matrix. And you can see here, this is the reward matrix in between the transitions, in between the states S and S prime. So that's why it will be represented in a matrix form like this, where you will have S and S prime here. So basically each of these entries corresponds to a reward obtained when transition to the next state. So all these entries will be giving you the value of the rewards when you transition from this state to next states, which are 1, 2, 3 or n, which we are denoting as S prime here on the horizontal axis. So if you make a transition from first state to nth state, then that will be corresponding to this reward R1n. And if you transition from state n to state 1, then it is given by reward Rn, Rn, 1. So it will be a matrix actually. So what you are doing now is you are actually multiplying PSS with R to get this particular expression here, the first one. And then we have gamma times this transition probability PSS again, because it's multiplied with VS bar. And VS bar is nothing but it's a one-dimensional vector of the value functions for all these states. So once we know all these things, we can actually use this particular expression to write in matrix form like this. And now once we have this, we can actually take the value of V onto the left side. So we can move this to the left, and then we can use matrix algebra to solve for V, which is given like this. So once we have this expression, we can immediately calculate the values of V, that is the value functions for all these states. Whereas in the case earlier, we were doing these type of episodes to approximate the value of V, and this can be done easily using this. So let us calculate the value function which we have defined over here for this particular example in Google Colab. And note that here the rewards are the rewards which are denoted by R of S, S prime, and not R of S, because there will be a difference in the representation in matrix form once we go for R of S rather than going for R of S, S prime. We will see this in our coming slides. But before that, let's implement this in Google Colab and see what is the value function for all these three states. So now this particular piece of code is basically the implementation of this Markov random process which is given over here. So let us start coding it. So in the first cell, that the commands that we have are basically normally the imports that we normally do. First one is import numpy as np, and the second one is that from scipy library we are actually calling this function linear alg. I will explain what's the importance of this in the later part of the code, but these are the two things that we are using to import. So let me run this. So now once it's executed, now we are defining the transition probabilities of this Markov random process. So here you can see we have three states. If you recall, here we have three states here, right? A, B and C. So these three states along with the transition probabilities that we have, which is 0.6, 0.6, 0.2, 0.4, 0.4 and 0.8. So we will make a matrix of 3 cross 3, and we will appropriately fill these values wherever it is present in that matrix. So this is basically done over here. If you see, we have the number of states equal to 3, and then we are defining the state transition probability P underscore SS as we are initially defining it with zeros, and it's a matrix of size 3 cross 3, and we are defining the float 32 as the size of the elements that we have in this matrix. And then we will be filling up appropriately the transitions which Markov random process is doing with these values. These are all transition values. So let me execute this first. So now once I have executed this command, let me see what are the elements of this matrix. So you can cross verify yourself that these values are as per the values that we have over here. So these are the transition values which you can see here, so earlier there was a slight mistake. It was not as per the if you recall my earlier lecture, here we made some correction. At this location it was earlier 0.6, and then it is not 0.6 actually, here it is 0, and then 0.6 is on the right side. So what I have done is I have actually made this correction in the code also. So earlier it was not correct, so this is the right one which is now present over here. So now if I execute this, and then if I execute p underscore ss, then what I'll get is this particular matrix, which is the same as the matrix that we have over here. So this is the transition matrix that we have over here. So now this particular equation is trying to check whether the columns of this particular matrix is actually obeying the property of this transition matrix, which is, that is, if you sum the columns of this matrix, its value will come out to be equal to 1. So it is just trying to check that, and if it is not, then it will throw an error. So let me run this. So it's not giving any error over here, so that it clearly indicates that the transitions that you are making for a particular state to all the other states is equal to 1. That is sum of the transitions. This we have already discussed earlier. So this is just for checking whether the matrix is obeying that property or not. Now we have the reward matrix. So if you recall earlier, when we were discussing Markov random process, at that time I created a reward matrix, and this reward matrix will be actually nothing but it's a 3x3 matrix, and let me show you that. So if you see here, so it is a reward matrix which is of size 3x3, you can see over here. So basically you have to write the reward values for the transitions that the agent is making in between S and S prime. So here you can see, for the first case, when the transition is from A to B, the reward is 0. So that 0 will be over here. And if I go from A to C, the reward that agent is getting is 7. So I will keep that value over here. And likewise, you can fill up all the other values, and you will get the matrix representation of the reward, which is RSS prime. So what I am doing over here is the same thing as you can see over here. So this is basically the reward matrix that we have, which we are defining by np.0, and the size of that matrix will be the size of the states that you have. So in this particular case we have 3x3, so 3x3 states will be there. In this particular problem we have 3 states, so the reward matrix will be of size 3x3. Then we are defining the individual elements of this matrix, and so let us run this. So you can see this is similar to what we had defined in case of theoretically over here. So once we have this reward matrix, now what we have to do is we have to actually compute this particular equation, and precisely in order to calculate this is exactly the same as this equation, but with the value of v manipulated. So we have discussed this already. So in order to calculate the value function for all these states, we have to actually solve this particular equation. So let us see how we can implement this. So first of all, we will focus on this. So if you see, PSS is a matrix of 3x3, and R is also a matrix of 3x3. So when you will multiply these two, it will give you a matrix of 3x3. So let us see what that is. So here what we are trying to do is we are trying to find out that. So here it is P underscore SS times the reward underscore SS. So this is basically what we are trying. So this is basically the implementation of this thing. So once we get the multiplication of these two, what we are trying to do is now we are actually summing up the elements along the columns here. So why we are summing up along the columns? We are summing up along the columns because if you see the equation corresponding to the value function, so you will see that we are actually summing up along all the futuristic states S prime. So all the futuristic states S prime are along the columns. So if you see here, all the columns will have the futuristic states S prime. So we are actually summing up all along the S prime in order to implement this equation which is over here. So that's why we are summing up along the columns which is given over here. Here x is equal to 1 is actually doing that. So then we will be actually printing up the expected reward. Expected reward is nothing but it is so this is basically your expected reward. This is expected reward. So what we are saying over here in this code. So let me run this. So this will be the expected reward that you will get. And now in this particular piece of code here, what we are trying to do is we are trying to implement this equation which is given over here. So we are implementing this now. So we have already calculated this. Now we are calculating this, and let us see how we will do that. So this is basically an identity matrix of size 3 cross 3. So that's why we have created the identity matrix which is over here. So this is basically the identity matrix. So np.I is nothing but it's a matrix of value 1 in the diagonal elements, and the size of this matrix is 3 cross 3, and then we are subtracting it with gamma times the p underscore ss. So gamma times p underscore ss is nothing but it's this particular thing. So somewhere we are actually implementing this particular thing, and we are calling this as a here, which is given over this side, and this we have already calculated, which is we are calling it as b. Reward expect we have already calculated over here. So this is nothing but it's b. So now what we are doing is we are actually calling a function linear elg, which actually takes two arguments a and b, and what it's trying to do is it's actually trying to solve this particular thing, which is ax equal to b. So it will try to find out the value of x from this system of equation. So once you keep the values of a and b here, then it means that it is trying to solve x is equal to a inverse b, where a in the first argument will be actually used as a inverse. So that's why what we are doing here is we are actually putting the argument a comma b here. So a is somewhere, it will be a inverse now, and then you have b. So whatever value that you will get by solving this is nothing but its value of x, which is given over here, and x is nothing but it's a value function which is given over here. So once you evaluate the value state, the values of that will come out to be 40.64, 30.28 and 44.54. So these values are nothing but in the long run these values are nothing but its value is 40.64, this value is 39.28, and this value is 44.54. So if you do a long simulation, then like the one which we had done here in this particular example, which is over here, if you do a long simulation and then calculate the Monte Carlo estimate, you will get the same values of the value function. But here you did it using the Bellman equation, and then Bellman equation specifically for Markov random process, and then the values that you got is 40.64, 39.28 and 44.54. So this finishes off with this particular example of Markov random process implemented using Google Colab. Now this is basically another Markov random process shown over here. So here the difference from the earlier version is that now the rewards are with respect to the states. So here it's like it is r of s rather than r of s comma s prime. So it's not this one, it's this one. So this is the only difference in between the representations for the reward. So if you look back here, so here basically the rewards was r of s comma s prime, which is this one, and here it is r of s. So that is the only difference. So but this creates a difference in the way we actually formulate the equation for calculating the value function. So if you see here, the rewards are indicated above in the format of R bracket S. So we basically are using now a column vector for representing the reward vector. So earlier, if you recall, we were using actually the matrix to represent the reward, but now it will be a column vector because the reward is basically depending upon the state rather than in between the state transitions. So as a result of which, this matrix will actually collapse into a single column vector for reward. So that is the only difference which actually changes the dimensions of these matrix multiplications. To be specific, what we are currently looking at is this version of the Bellman equation. So you can now easily understand why RS is outside the double summation, which was not in the earlier case. So the reason for that is because reward is basically now a function of S rather than that of the S prime. So we can represent this particular equation, which is given over here, in matrix form as this. And here you can see now we can similarly get the value function for all these states by using this equation, where what we have done is we have taken this factor to the left side and then inverted this complete expression over here. So now what we will do is we will actually take one example where your rewards are depending upon the states rather than that of the intermediate transitions. So in particular, we will be taking this as an example, and here we will, if you look into this Markov random process, then what you will see is all the values which are given in blue are actually the rewards, and they are within this, they are defined in such a way that it is basically nothing but R of S rather than R of S comma S prime. So you note that for each of these states we have the rewards associated with that. For coming to home, back is basically given the reward 0, and this is basically the transition probabilities which we have for when a state moves from one state to another state. So these are the transition values for this Markov random process. So let's basically code this in Google Colab and see what will be the value function for all these states. If you see the matrix representation, then basically states are represented as a one-dimensional vector, which is given over here. So we have all these states which are defined here, that is first Coke, then food, enjoy with friends, last Coke, and then Coke, continuously taking Coke, and then home, coming back to home. So all these are the states which are already defined in a one-dimensional vector. Now recall that now as we had discussed earlier, the rewards will be in the column vector, so it's like this and not in the matrix form as it was in the earlier case. And then we have this state transition probability PSS prime, where you are from state S moving to state S prime. So you will be filling up all these probability values inside by looking into this Markov random process, which is given over here. So you can see for each of these interstate transitions the values, and you can put that values over here, which is given over here. So now I hope you are pretty comfortable in how to fill in these values of the state transition, because we have already done it earlier so many times. So once we have this and this, then what we can do is we can actually use the equation which we had discussed earlier. The equation which we had discussed earlier to implement this particular Markov random process in Google Colab. We will calculate that value and see whether that value will come out to be the same as the value which we are calculating now in this particular slide. So let us say what we will now interested in is to calculate the value of Coke, which is given over here. So what I'll do is I will try to find out the value of Coke and check whether the value of value function of this particular state, which is Coke, is 0.96 or not. Another point which I missed out is the values which are shown in this purple color. So if you see here, all these values which is like 1.09, 2.06, 0.96 or -3, and then you have 1.12. So all these are value functions for the states which is already there. So we have already calculated these value functions. So what we will do is we will check these value functions whether they are coming out to be the same through the programming or not. But for example, if we want to calculate the value function for this particular state, which is like enjoying with friends, with the value of which is given as 1.09. So let us see how we are getting this value of 1.09. So what we do is actually we are calculating the value function of the enjoying with friends. So that is equal to the RS, that is the immediate reward that you are having of being in state with enjoy with friends. So whatever immediate reward that you are getting in that, plus gamma times the state transition times multiplying with the value of the state functions in the futuristic states which are S prime, and you are summing up on the all the futuristic states S prime. So here the immediate reward that you have while being in this state of enjoy with friends is 1, as you can see over here. So this is 1 here, plus gamma we are taking as 0.1, let us say. Then what we are doing is we are actually multiplying the state transition probabilities with the futuristic value state functions which are connected to this particular state. So if you see here, then what we have is 0.4 times 0.96, 0.4 times 2.06, and then we have 0.1 times -3. So basically what we are doing here is we are actually adding up all the state transition probabilities with the value states and the states which are connected to this enjoy friend. So what we are doing in fact is we are actually adding up all these values, and once you do this calculation, what value you will get is 1.09. So we will see in Google Colab when we will implement this Markov random process that whether this value of 1.09 is coming or not. So this enjoy with friends is nothing but it's basically a specific state for which you are actually calculating the value function, and all these S primes are basically connecting states to this S. Basically what you can do is you can actually do summation on all these states, but the problem is all these states are not connected directly to S, only few of them are connected to this PSS prime. So that's why you have only 3 terms coming into play, and the rest of them will be all 0. So in short, you will always sum up the futuristic value states only for the ones which are actually directly connected to the state for which you are calculating the value function. So let's go to Google Colab and see whether we are getting this value of 1.09 or not. So now in this example, if you see here, we have 6 states. So you can see 1, 2, 3, 4, 5, 6. So there are total 6 states. So what we are doing is we are actually putting 6 states over here, and gamma we are taking as 0.1 in this particular situation. In the earlier case we took gamma as 0.9. Please note that here we are taking gamma as 0.1, and this you can easily write the state transition matrix which we have already discussed in the last slides. You can write down easily by looking at this Markov random process here. And then this is basically an implementation of this equation which is given over here. So I minus gamma PSS, the whole inverse, you are calling it as not the inverse, you are calling without that as A1 here. And then the reward matrix, which is now it is defined as an array which is given over here, and then we are making it as a column vector using a reshape command, and we are feeding it to the variable b1 here. So please note here, now the reward matrix is not a matrix, it's an array here, and the reason for that we have already discussed, because right now here you have this which is a column vector, and you know that value function will be also a column vector. So you want the right side of it to be column vector, so that's why your reward matrix will also be a column vector. And the second reason for this being a column vector is that there is no intermediate S and S prime transition reward which is given. It's an absolute reward which is already given. That's why we are defining it as a column vector. So now we will be implementing this equation which is through a lin-elg function which is there in SciPy. And once you calculate this equation, you will get the value function for that particular state. So here if I run this, you can see here we are calling lin-elg.solve for solving through A1 B1, and then the results of that will be the value state. So once we run this, let me execute this first, followed by this, and now I'll run this. So now you can see the value which you are getting over here are the value functions of the states. And the important thing is that we calculated the enjoy with friends, which is basically the second state, and the value of that is 1.09. So you can see over here which we had already calculated. So this is 1.09 and this is nothing but it's a second state. So the value function corresponding to that state will be the second location of the one-dimensional column vector. So here you can see its value is coming out to be 1.09. So we cross-verify our calculations with that calculated theoretically using this equation which is given over here. So I think this completes the full understanding of Markov reward process. In the next chapter we will discuss Markov decision process and then we will move forward. Thanks.